Okay, so now everything is okay. I think you heard, though, what I said before. So the beauty of it is that it's always there. And what's the frequency? It's twice the rotation frequency if this is the mechanism. Move. Okay. Question is, all right, what could generate such deformation? Various mechanisms, some more hand-wavy than others. Neutron stars are born in a messy process, core collapse supernovas, and it's very unlikely that this process is perfectly symmetric. So one can imagine that there is some deformation that's frozen in at birth. We know, on the other hand, that pulsars are not these pristine objects. They are subject to starquakes, perhaps. So there's signs that the crust is subject to readjustments. Okay, so mountains could be formed during such events. If the system is accreting, it's very interesting because the accretion is funneled through the magnetic field lines and it's accreted in one spot. So there's, that's definitely an asymmetry, and a variation of temperature and density in that spot, and the material piling up could perhaps generate deformation. And then there's internal magnetic fields that could deform the star. So question is, all right, how big can this deformation be? And the problem is that nobody knows. The answer varies by orders of magnitude. So plausible values are lower than 10 to the minus 3. Given our observational constraints now, I would say pretty surely lower than 10 to the minus 5. But if, for example, the deformation was sourced purely by an internal magnetic field of 10 to the 7 or 10 to the 8 Gauss, so then the ellipticity from that could be as low as 10 to the minus 14. So there isn't enough work going on modeling this, and it's complicated and nasty. So why bother? Well, because the value of the ellipticity could tell us something about the structure of the neutron star, the internal structure of the neutron star. And in fact, this range of variability in the predictions, even just of the maximum ellipticity that the neutron star could support, stems from not knowing really what phase of matter is inside the neutron star. So if we did detect something that suggested the ellipticity was 10 to the minus 4, then people would need to start thinking hard about some exotic equations of state. Also, the galactic population of neutron stars, because as you will see, the type of signals I'll be talking about, we're not going to be able to detect them in the foreseeable future to megaparsec distances. These are galactic signals. So the galactic population of neutron stars are 100 million objects, of which from EM observations of pulsars, we know a few thousand. Now, this could be a way to access, perhaps, some of that invisible population. The signals are always there, which means, and I will make this a little bit more quantitative, we can really pin the signal wave shape and the parameters, the signal parameters, pretty well, which means that this is perfect for fine tests of the wave shapes and hence tests of GR. Basically, these signals are the gravitational wave equivalent of pulsars. So imagine all the tests of GR done with pulsars, we could do them with a different probe. If in conjunction with electromagnetic timings, because the gravitational wave frequency, the relation between the gravitational wave frequency and the rotation frequency encodes the emission mechanism, we could learn, for example, about the emission mechanism, whether there's differential rotation between the bulk that's emitting the gravitational wave signal and the outside that's emitting the EM signal. And of course, there's the possibility that it might not be a neutron star at all emitting, but I won't talk about this here. So how weak are these signals? If you plug in reasonable numbers, so a 10 to the minus 6 ellipticity, a gravitational wave signal of 1 kilohertz, and I put the star at 1 kiloparsec, you get a signal that's 10 to the minus 25. And that's, 4 orders of magnitude lower than the signals that we currently detect. So this is the situation. So how are we going to detect something like this? Well, the simplest way to think about it, the signal is always there. If you have a sinusoidal signal, how do you detect it? Well, you observe for long enough that if you take a Fourier transform, take the square modulus of the data, you see the peak at the frequency of the signal. It's a little bit more complicated, but that's basically the essence. So where to start looking? Known pulsars. We know their frequency, their frequency evolution means the frequency derivatives. So we think, well, the gravitational wave mission is phase locked because it comes from the rotation to the EM timing, so frequency derivative at twice though. So the signal is known and searches are done for every object whose rotation frequency is such that the gravitational frequency falls into the LIGO band. Every, let's say, big data set, LIGO, Virgo, Kagra do these large campaigns. So far, no detections. As for all the various scenarios, unfortunately, I'm going to review. And so what we can do, though, is place upper limits, which means what's the largest gravitational wave amplitude that's consistent with our null result. Since we haven't observed anything, we can exclude any gravitational wave amplitude larger than what we know we would have been able to detect. And these upper limits, so have this quantity, the upper limit on the gravitational wave amplitude, as a function of the signal frequency. And obviously, the lower this curve is, the more constraining are our upper limits. As an important benchmark to understand when do these tell us something that we didn't know before? And it's the maximum amplitude that I could possibly expect for that signal, which is the so-called spin-down upper limit amplitude, which is the amplitude that I would expect where I'm sitting at a distance d from the source, such that all the rotational energy that is lost by the object that I know, because I know F and F dot, the rotation of the object, were carried away by gravitational waves. We can hope for no more than that. So that's the maximum it can be. And our upper limits start becoming formative when they're lower than that. So this is a paper from 2022 put out by LIGO, Virgo, Kagra. No, at the time only LIGO, Virgo. And there's a very recent one that came out, but it only looks at a subset of pulsars. This is the largest set of pulsars that's been examined. This is our upper limit plot. It's busy. Let me walk you through it. The results are the stars. Okay, so for every target, every pulsar, there's a star. That's the upper limit. And also for every star, there is a triangle. That's the spin-down upper limit. And so the ones that are interesting are the ones where the star is below the triangle, because it means our observations are becoming informative. And they're the ones that have got this circle around them and these green lines. And so we see that there is a bunch of them, but don't get too excited, because if we look at these upper limits, not as upper limits on the amplitude, but as upper limits on the deformation of the objects. Here, forget about these lines and concentrate again. Results versus the ellipticity that would support emission at the spin-down limit. We see that the ones for which the upper limits are informative are also ellipticities that are very high. So really, yes, okay. we can constrain, let's say for the crab here, the amplitude to be a factor of nearly 100, actually 100 times smaller than indirect upper limit. But that indirect upper limit would have implied an ellipticity of 10 to the minus 3, which is physically very implausible. And so we have this situation where the object for which this happens, which are the most interesting in principle results, don't have really large values don't have really physically very interesting values of the ellipticity. These are very high. And the ones for which the constraints are numerically low, interesting values, we knew a priori that the objects were emitting obviously very, very weakly. There's an exception here for this one, okay? So it's been monitored particularly carefully. So this is the situation for, you know, the obvious search, which is the one for the objects that we know of. There's objects that we know of here, this one. This is Casei, young supernova remnant. And I was saying that, you know, what could possibly generate the ellipticity, the deformation? Well, just the process that generates the neutron star. So why not look at the central compact object that's supposed to be and suspected to be a neutron star at the nearly center of young supernova remnants, and particularly close by ones. So these are searches that are more complicated than the ones where you know everything, because for an object like this, we know the position pretty well, but we don't know the frequency or the frequency derivatives. We don't know how fast the object is spinning, which means that now we have to search over different combinations of frequency and frequency evolution parameters. So these are searches that require a lot more investment of resources. Other objects that are interesting, again, referring to what could possibly generate the ellipticities, are neutron stars in accreting systems, LMXP most notably. And that is actually an interesting observational fact, that if you look at the spin frequency of these objects, you see that there is a sharp cutoff just above 700 hertz. There's no neutron star known to spin higher than 720, 750. Whereas we know that in principle, a neutron star could sustain rotation frequencies much higher than that. So why is that? And that's so sharp. Well, the idea that's been around for quite a while is that there is some kind of mechanism that balances the accretion torque. And a mechanism that would do that effectively, so effectively as to create quite such a sharp cutoff, would be gravitational wave emission. So the gravitational waves are balancing the accretion torque, okay? So here, there's not just the idea that the object is accreting, so there's actually, you can imagine physical reasons for which, you know, there could be this mountain or non-symmetry, but there's also indirect evidence that indeed it could be gravitational waves. So we do search for emission from LMXBs, you know, to balance the accretion torque. The more accretion you have to balance, the higher is the gravitational wave emission. So the most promising systems are the ones that are emitting a lot, because the X-ray flux, you can sort of equate it to the mass accretion rate. And what's the brightest X-ray source in the sky after the sun is Scorpius X1, so that's one of our prime targets. Searches are done. Again, there are searches over frequencies, spin down in principles, but also over the orbital parameters that are not so well pinned down. So auxiliary observations, please, yes, do observe SCO-X1 and give us more precise parameters, because this allows us to broaden the searches in other directions. We are just about definitely starting to probe the torque balance value of the amplitude, but still haven't detected anything. But here is really a place where if we know better the orbital parameters, then we could go deeper. Okay, how about signals from sources we don't know of? There's a lot of them in principle. And so why not a blind search over any position in the sky? Now, if you want to use the optimal search methods, you're going to have to combine coherently the data from all the detectors that you have over a year or more of observation. And when you do this, you have to do that for every single sky position and assumed signal parameter. And since the resolution increases in all dimensions with powers of the observing time, this search over even 6 months of data is completely undoable. So we have to resort to other methods. They're called semi-coherent search methods, where we basically do coherent searches, but over only shorter stretches, and then we combine them together. There's a whole class of different searches of this type. And then that's not just it. We do a whole hierarchy of these semi-coherent searches. We do the first pass with relatively short coherence length, because this is where we have to survey the entire sky. And then we select the waveforms that appear more promising, and with those we look at them more carefully with, increasing sensitivity and increasing also cost per waveform. So what happens basically is this, and this actually has a signal in here. At the first pass, I just select as many as I know I can follow up. And then at the second pass, only a few will survive. And at the end stage, the only surviving candidate is the one that is a gravitational wave signal. So from the point of view of the signal, it's like a zooming in, okay? As I said, there's many, many different ways to do these. These are suboptimal methods. So it depends really what you're aiming for along 3 dimensions, which is either breadth of search, depth, or also robustness with respect to deviations of the signal waveform from this perfect, ideal, perfectly coherent signal over months and months. My group, since 2018, left the LIGO Scientific Collaboration. We wanted to be more agile, and we think diversity of approaches is good. And so we have to wait until the data is released publicly. That's why this is a topic that's dear to me. So we have to wait 2 years. And so we really had to go to searches that were very deep with reasonable compromise, actually very respectable, though, breadth. And I'm going to use our latest paper to illustrate how many stages one such search can have. So here we had actually 10 stages. And you see here, this is the number of waveforms surveyed and the one that survived. So we start with nearly 10 to the 19 waveforms, even with a semi-coherent method. And then up to stage basically 7, so the 8th stage, we go to fully coherent. We had 54 waveforms that had survived, and we can get rid of 12. Then we take new data, and of those 12, 6 survive. And then we combine the 2 data sets together, again, fully coherently. And those 6 continue to survive. But unfortunately, those 6 are not real signals. They're actually fake signals that LIGO injects by moving the mirrors for validation purposes, okay? So it's very cool because we detected all of them, and we did it not by tuning the analysis to this, was really after running our analysis, these were the only ones that survived. And okay, how did we recover them? So these are the signals that we recovered. This is the frequency derivative, and this is the error that we made. And so look at our resolution in frequency. We got the frequency wrong by 1 × 10⁻⁹. That's the largest hertz that we made. And the sky distance, this is the difference between us and the transient signal, is sub-tenths of seconds, okay? So this is really a different, it's not transient astronomy, it's the gravitational wave pulsars. And this is the promise of it. So one question is, if at some point we detected something, if something survived my pipelines that was not one of the fake signals, which I sincerely hope to live to see, how are you gonna inspect that spot in the sky? Who do we turn to? Of course, we turn to our radio astronomer friends, X-rays, gammas, but, perhaps it's not a pulsating object. The beam is not pointing towards us. These are things that could be, a kiloparsec away, but they could be even 50 parsecs. So perhaps that's something to ponder. And these are the upper limits. These are the upper limits from this search. And you see, in order to be complementary with these LIGO collaboration, Virgo collaboration results, we had to do this very deep search, and we are at the level of about 7 point something × 10⁻26. That's the gravitational amplitude that we could have detected. What does that mean in terms of ellipticity? Well, you have to say the source is at a certain distance. And so let's take a distance of a kiloparsec. For signals above 300 hertz, we can exclude sources with ellipticities 10⁻⁶ and larger, which is, I think, quite impressive. It tells you these objects are really round. How did we reach that sensitivity? Well, we had to use Einstein at Home, which is a volunteer computing project that we set up to help us do these searches that are very intensive. That's for the stage 0, the first stage where we have to survey the entire parameter space. But it's also the stage that, if we lose something at that stage, there's no follow-up that's ever going to recover it. And please, some advertisement, consider signing up. And if you have idle cycles of your compute clusters, they're fantastic queue fillers. Don't keep them idle. Donate the cycles to us or your laptops, your department. But you don't need to have Einstein at Home to actually do continuous wave searches, because we've also released the atlas of the continuous wave sky that allows you to execute new searches based on the results of our searches, ones that we even haven't had the time to completely follow up. But you could correlate these atlases with your observations, complementary observations. So this is, they just disappeared, I think, what was it, less than 2 weeks ago. And this is the QR code for downloading the atlas. The situation gets even worse if the signal you're looking for, you assume comes from not an isolated neutron star, but a neutron star in a binary. Since you don't see it, now the question is, what are the orbital parameters? And so the thing that people do is that, well, they look at neutron stars. What orbital parameters? These are projected semi-major axis orbital period of known neutron stars. Let's start by surveying the whole sky with boxes that cover where we know that neutron stars are, that pulsars are. And unfortunately, when we do that, due to the increased parameter space, our sensitivity suffers. And so here I show upper limits from two searches, these two boxes. And what I want you to take away from this is the ellipticity upper limit, is first of all, the smaller frequency range. You just cannot do computationally more. And also the fact that the ellipticity upper limits, I know you can't remember the, the numbers, but they're factors of a few less constraining on a smaller parameter space. So, you know, there's no way around this. If you pull the blanket in the direction of breadth, you're going to suffer in depth. And for this, to really tackle it, I think we need, you know, new and clever methods. There's no way around it. So, summarizing messages is, I would first of all encourage you to think about the fact that it's not just transient continuous gravitational waves. Hopefully, we will soon see also continuous gravitational waves. It could be that the first detection that we have is not a gold-plated one, like the first gravitational wave binary black hole. It might require some ancillary support, like an electromagnetic counterpart. How would we go about doing this? How would you, with your telescopes, go about helping us to support or, you know, say, well, we don't see anything? We are probing interesting parameter ranges because these ellipticities are physically plausible. Broad surveys are hard and trade-offs are necessary. And there's an entire class of sources that we really can't do as well as we do for others, like the binary ones. And these are important because fast-spinning pulsars are mostly in binary, or by half of them are. So there's open problems. More modeling is also required to guide the observations and guide these trade-offs in terms of parameter space to search, and hopefully also in the near future interpret observations. And you know, this is a high-risk, high-gain enterprise. I skipped through the slide where I said, what are the chances of detection? I can't guarantee you that we'll see a source with advanced LIGO. I can tell you that the chances are much better with the next generation of detectors. But, you know, I was around when we weren't detected anything for decades. So we should remember that investing in these is necessary. And I guess I'll close with the quote from Maxwell that, you know, the only guarantee of failure if we don't try. Thanks.
Very much, Maria. Are there any questions? There we go. Any questions in the room?
Thank you for the very interesting talk. I was wondering if you expect shifts from the neutron star axis symmetry when you showed the, you know, the little protuberation on the neutron star surface. Do you expect this to affect precession? And if so, do you take that into account when looking at gravitational wave signal?
Mm-hmm. So the precession measurements are very hard. And at these levels of very low ellipticities, it's not, there is no, you can't really use the precession to infer the ellipticities at values, you know, 10 to the minus 6 or 10 to the minus 7.
Thanks.
A quick question on these hardware injections that you found. So these are still present in the public O3 data? Did I get that right?
Yeah, they are. In fact, when you release the any LIGO or Virgo data, in the release pages, there is a link to hardware injections, and they're divided in categories. And so you can see all of the continuous waves.
You showed the nice position of the ones that you detected.
Mhm.
Are there also ones that you missed
Okay.
to pick back up?
Okay. So these are the hardware injections in the range of the search. So these are. So these are our upper limits. So the one that we missed is this. So it's just barely below our upper limit. So it's consistent. But you could say, all right, but you've detected these ones that are so below. So why? How's that? Well, obviously, this is a population average upper limit. Population averaged over what? Most significantly, the inclination angle. Okay? You detect much better things that are face on rather than edge on. So you could say, was this edge on? Actually, no, it wasn't. The reason why we missed it was that it fell very unluckily just right in between our spin down value grid. But it was still, it's still consistent with our upper limit. But in fact, you see, since these are 90% upper confidence, we can even detect a lot of sources below. And these were the only ones in our search range. And I believe this is the only search that achieves such high recovery of the injected signals.
Yeah, thank you. It's a really interesting talk. You might have said that right at the very beginning I had a technical issue to deal with, or maybe you did say it. Sorry if you did. I was thinking about these neutron stars that are asymmetric. So something like, have you thought about FRBs, fast radio bursts?
Yeah, we have, but they're so far away.
Yeah, true.
Could we have, one within 8 kiloparsecs at least?
Okay, so it needs to be that close.
It needs to be that close. You see, this is 8 kiloparsecs. So we see ellipticities, which, are in the 10 to the minus 6 range, only for frequency above 300 hertz when we are as far as 8 kiloparsec is, this scales linearly with the distance. So it becomes uninteresting, basically, if you go.
So I guess the soft gamma repeater in our own galaxy that looked a bit like an FRB could be a test for this sort of thing, possibly.
I guess.
Yeah, who knows?
Well, I mean, the All Sky searches cover that location too.
There's another question here.
Thanks for the very nice overview, Melissa. Could you comment on the prospects of observing pulsar glitches in current or particularly future detectors, and also prospects of what we can do in terms of science if one is observed in both EM and gravitational waves?
Well, so first of all, glitches, that affects this part of the axis, because for searches like this, that's really, really very sensitive. You remember here, what I do at some point is I do a fully coherent search. So that means that I am assuming that the signal is perfectly phase coherent over the entire, let's say here, first half of O3, then separately on the second half of the O3, and then over the entire O3. So if the object glitched, it would have possibly been discarded in these last. So yes, we're very sensitive with that caveat. So that's where, we've made that that choice. Now, what happens when you give up some of those assumptions? Well, your search methods become looser. They're more forgiving, which means, though, that you're less able to reject noise artifacts. And so, from the same data sets, these are these less stringent upper limits. Now, these are still, however, I mean, there was nothing significant, even from any of these searches, the ones that were more forgiving towards deviations from the completely phase coherent stage. If something had survived, then of course, it would be good to start targeting that sky position and see, do you observe something? Is it a pulsar? First of all, is it a neutron star? If you see already pulsations, that would be a smoking gun. Then, of course, you could add and information about glitches. But just if you have that, if you have the rotation frequency, the gravitational wave signal, then it would be very interesting to see if there is, around the time of the glitch, a difference, or shortly after it, between the two frequencies, because the glitch mechanism is that the superfluid core is pinned to the crust, but the crust slows down. At some point, these unpin, and this is what this transfer of angular momentum produces the observed glitch. But the superfluid core perhaps does something different, and that could help elucidate that.
Thanks a lot.
Any other question? No other question? Okay, we are right on time, so we can